So I'm going to be talking about, over the past year, we've been leveraging ROS to deploy some scan and plan systems based on technology we've developed over the past few years. So I'm going to cover the evolution of scan and plan. There's been several milestones of that FTP project that was had several participants from the ROS industrial community. And then I'm going to talk about how we took that technology and applied it to production, several production systems, give an overview of those systems, and also go over some of the challenges we had in taking a technology that we developed in our labs and actually deploying it to a production system, and the solutions we came up for that. Also give an overview of the different technology that was leveraged during that development, and then we've been creating some example work cells to make available to the community as a baseline for this type of technology. And then based on the work we did, we learned a lot through that process. So I'm going to give a brief overview of some of the active research we're doing to take what we deployed and improve upon that technology. So the idea of scan and plan was you had an unstructured environment. In most cases, you didn't have the CAD model. So you needed to scan the part, perceive the part, do some processing on it. And once you've got the representation of the part, then you execute some type of process on it, whether it's inspection, grinding, painting. And then following that, then you will need to do some type of inspection after the process, and you iterate on that. So the scan and plan project started back in 2014. You can see the example cell there. It was using the first generation or the second generation Connect. It also had a line scanner for doing inspection. And the system was set up similar to what you've seen in the production system. There was a user input that we did some type of scanning. There was feedback to the user. They provided some input. And then following that, then generating robot trajectories and execution, and then some feedback to the user. Then in 2016, we actually took a little bit step further. We actually put it on a larger industrial robot using an industrial sanding head to do some type of sanding process. And then here recently, over the past year, we've been working to deploy a multi-purpose cells that do stripping, sanding, painting on large gantry systems. So I'm going to give one of the production systems. I think this was the first one that we worked to deploy with an integrator. Our participation in that was taking our scan and plan technology and then applying it to their system and working through the issues of taking something in the laboratory and putting it in a production environment. It had a 2-axis gantry, 6-off manipulator. The range of that gantry was 6 meters by 4 meters. So it was quite large space that we had to use. So the first component was they didn't have CAD models of these parts. So we needed to create some type of user interface that allowed them to scan the environment, extract the part from the environment, and then provide some user input on that part. You saw a video earlier where the user was able to adjust different parameters as far as like raster spacing, point spacing of the Cartesian poses, and those type of things. So, and the other step that wasn't shown there is we also needed a way to recall. So if we found that if something happened in the production facility, how can we recreate it on our end to troubleshoot what was going on? So we created a database management system. So every type of action that was done, the information that was passed between different nodes in the system, we were logging this information in a database, the inputs and outputs. So at any point in the stage in this production system, we could recreate that exact state, troubleshoot it, provide patches to the software improvements, and give that back to the user. And then there was a whole online process after that. So that was the offline. The online process was doing the part selection from a predefined database, scanning the booth, perceiving the scan data, doing localization, localizing the part in the environment. Once that was done, we would do a detailed scan of the part, so we would be able to get closer to the part and do a more accurate scan of the part. Then we would do tool path generation, robot trajectory generation, and then we provided all that information back to the user where they could make different tweaks and changes based on their understanding of the process and make minor improvements. Once they were okay with it, they would approve it, and then it would execute it. And then we had a whole bunch of logging on that. And there were some other things that we'll talk to later, like the manipulation tool, and then also contact monitoring. So one of the things the user wanted to do is, since they were already at the computer, they didn't want to have to go and jog the robot, do things like this. So we provided an interface to them where they could manipulate the robot both in Cartesian space, dragging the tool TCP around, but they could also manipulate the individual joints, provide feedback, and then execute motion plans to that from this PC. Another component to it was this cell was very large, right? It's very difficult for the operator being outside the cell to see if he's going to run into something because he's so far away. So what we did is we implemented a contact monitor that was reading information from the robot and actively running collision checking. We were able to achieve about 80 hertz, sending that information to the PLC, and they were able to define some type of contact threshold, and you can kind of see this. So the yellow indicates that I'm getting close to my contact threshold. Green is you're outside some type of nice region. If it gets the red, that's when it would send a signal. The PLC would stop the robot. That way the operator, you had some assurance that the operator wasn't going to collide with something in the environment or itself. And most of the challenges we ran in deploying this was the system shown on the right, was taking the physical world and mapping it to software, right? One of them is festooning. How do you represent that, where it's wrapping up or going to catch? Also, this system had a lot of DCS zones, so on a lot of industrial robots, you can set both no-go zones in joint space, but you can also set no-go zones in Cartesian space. And then how do you represent those in a way in software that you can avoid those, but still satisfy your process constraints, like smooth joint motion, maintain velocity, and things like that. So a lot of the challenges we had was taking those type of constraints on the process and mapping them back to our motion planners to achieve good robot trajectories. And then error recovery was like when a motion planner fails, what do you do? How do you change that? Because we wanted it to more or less not have to require a whole bunch of user input. So we had to implement a lot of intelligence in the process planning framework, which I'll go into a little later on, explaining the type of things that we did to improve the performance of our process planners. So some of the technology used, for the high-level state machine that was managing the overall system, we used the tool that's provided by QT. It's a SCXML standard for state machines. The nice thing about this is it has a whole GUI representation, so you can view the different states of your system in a GUI, and it maps to software pretty nicely. So C++ based, but it was very nice for laying out the overall states, seeing the flow of information. You could also see what state the machine was in within this GUI framework. And the other thing is it worked nice within our development environment, Qt Creator. For the scanning and reconstruction, we use Yak, which is basically it's another implementation of Kinfu. We made several improvements to it, knowing that a lot of our software, knowing that ROS-2 was on the forefront, we started separating our software such that we took the core libraries that really didn't depend on ROS components and separating those out into ROS agnostic packages. They're pure CMake. That way we can make them easily build on Windows, Linux, and other OSs. And also it allowed it to be reused outside of ROS or in other type of domains that it didn't make sense to use ROS. So we made a lot of improvements to this library and several others in a similar manner. The main library that we use for the toolpath generation, it's a ROS industrial package called Noether. It was developed under an internal R&D project that we had open sourced. It provides several functionalities for taking a mesh and generating tool paths on that mesh, given some type of criteria like point spacing, raster spacing. But as we were developing that, as you imagine, the meshes that come in from these type of scanners aren't maybe to the quality that is needed for a tool like this. So we spent a lot of time adding features into Noether to create this filter pipeline, where you could take the scan data that came in, or I think this mainly operates off of both scan data and mesh data. So it would take a mesh data in, and it would provide some type of filtering. So it would do smoothing, outlier removals, and also there's other features like B-spline surface reconstruction. A lot of these tools that we're using within this filter pipeline are built on top of PCL, which is the point cloud library, to build out this filter pipeline. You can see an example on the left where you have some point cloud. It fits a B-spline to it, but you also need to trim it, clean up the edges, generate something smooth that a robot would easily execute. Another component is because these are very custom processes, we've been leveraging Tesseract, which is a motion planning environment. It's similar to Drake, Dart, and MoveIt in those sense. It provides both ROS-I and ROS-II. The interesting thing about this is all of the core of it is ROS agnostic, and then it has thin ROS wrappers on top of it that allowed us to quickly deploy it both to our ROS-I systems and ROS-II systems. It also has a full Python interface for the core components of the library, so everything that you can do in C++, you can also do from Python. Most of that was from our work with the ARM Institute. We had a lot of university students that would prefer to use Python than C++, so we had a member that took the core API and exposed it in Python to make it usable by his students. So in a lot of this, in most of these processes, just not a single motion plan. There's a lot going on. So from Noether, you get a tool path, which is a raster on a surface. But there's other things that need to happen in your process. You need to approach the surface at some angle of attack. You may not need to be normal to the surface. You may need to be at some angle, and also departure. And then somewhere in the median, how do you transition? Are you going to do linear transition, free space motions between that? So we've been developing out this whole process framework that works with providing a raster in that will take that. You can provide different types of generators that will generate the approach and departure. So you can have just an axial approach and departure. You can have a parabolic approach and departure. But it allows you to custom define these different generators that allow you to adapt the tool path that came out of the mesh for different processes. So you can quickly run it through a paint toolpath generator, which then would take that and generate all the necessary components, the approaches, departures, transitions for paint, for sanding, grinding, and those type of things. So we've been spending a lot of work on that. And in most of these cases, you're not using just one planner. You're using multiple, right? So for Cartesian, we have several different planners that work well for doing Cartesian motion planning. And then we use different ones for free space motion that work better in that type of atmosphere. So developing that out such that you can define it just arbitrary Cartesian waypoints, and then it can understand how to break that process up and run it through the correct robot trajectories generators. This is an example of a scan implant system that we're working out as more of just a base platform that people could use and build upon. It's a 6-axis robot with a 2-axis external positioner. You'll see this part later today. It's on one of our mobile scan implants. For doing, in this application, we're doing a sanding process. But this will kind of show the process. So here we ran that part through Noether, which generated the tool path on the surface. We then run it through our process planner, which then adds the approach and departures at the ends of each of these tool paths. And then we'll generate robot trajectories for that. some of the things we learned is a lot of our process planner was very rigid, in that when we would do Cartesian space, we'd run it through Descartes, which is a sample-based Cartesian planner. It's globally optimum, but it has limitations with a lot of these. We found with a lot of these industrial systems, you can have thousands of waypoints. You quickly run out of memory on your machine, so you can't sample at the resolution you would like to get smooth motion, so we have to sparsely sample those trajectories. And then we run it through some type of optimization-based motion planner that has the ability to handle high degrees of freedom fairly easily, and it can handle velocity smoothing, joint space smoothing, and a lot of these other types of process constraints, and give you really nice trajectories out of it. And then for free space, we typically use OMPL as a sparse planner to get a rough trajectory, and then we also run it through our same optimization-based motion planner for free space motion. But those, at least in this production system we deployed, it was very specific to that system. It was doing X, Y, Z, and if that failed, we might try that same process over again and until it does, because there is some randomization, at least on the free space with OMPL. It's a random-based sampling, so you can sometimes just retry again, and it may successfully pass again. So we were trying to take that whole process planning framework, but make it a little bit more intelligent. So there's a nice library out there called CPP Task Flow that allows you to define a set of tasks and constraints on those, like what process has to finish before that to continue on with the next process. And then if that fails, you can do conditional type tasks. The nice thing is this is highly parallelizable. So this whole framework, you submit it, you tell it, I have 30 processes available, you can submit 5,000 tasks to it, and based on the constraints you set up on the task, it will execute it as optimal as possible. So it'll allow us to create more intelligent process planners. That way it just doesn't fail and then just stop there. It can actually, we can create some nice intelligent branches that if this fails, change some parameter and try again, or switch to this planner and try this planner if it fails, things like that. So this is in progress. This is something that we're developing to make more intelligent process planners to handle painting and grinding and sanding. Some current research work we have, we're doing some of the feedback from that is they would like to have more real-time adaptability to the motion plans to be able to adapt to the environment. So we're looking at what things need to change in our current framework to be able to accommodate that. Most of the time spent in our motion planning is during collision checking and evaluating those process constraints. So we're looking at TensorFlow and PyTorch for because it has both CPU and GPU accelerations that you can leverage both of those for defining our constraints on the system, like joint velocity, avoid collisions, and things like that. We're also looking at Bullet, which has the new Bullet 3, and they also have a GPU implementation of a collision environment for doing collision checking. So we're currently looking at those different components to see how we can accelerate this process planning framework. And this would then nicely lend us into doing some type of real-time control if we were able to get the collision checking and the evaluation of these process constraints to a point where we can adapt to them. Another thing we found is, as I mentioned, in Noether, we had to do a lot of pre-processing to the data that came in order to get good slicing of that surface. We came across a library that this is a heat method approach, that it had the ability to handle really noisy data, both point cloud and meshes and things like that, and generate nice ISO lines, evenly spaced lines on different types of data. So we're currently looking at this as maybe an improvement to our current toolpath generation. It's a unique approach, but you can kind of look at the way it works is on the subdivided surface on the left, you can see there's a center. They did a point heat source, and they could very quickly solve how, if you had a heat source there, how does that heat propagate through the data? And then based on that, they can, because they assume it's homogeneous, they know the distance at which it traveled over, and they create these really nice ISO lines on it. So we're looking at seeing if we could take this type of approach and provide like a heat source of a line along it, and then see how that line propagates to create tool paths. And that's currently actively being done. I think it kicked off a month ago. We have 3 more months of that project. So it'll be interesting to see how that turns out for an alternative to the toolpath generation. I think that's all I have.
Questions for Levi?
Yeah.
Amazing project. I was wondering if your work, what percent of the work would you say requires robotics knowledge about robotics, like kinematics, and path planning at the joint level versus software development?
So the question is how, I guess, percent of time required to, or I guess the knowledge required in relation to robotics versus relation to just software engineering. Motion planning required a lot, I would say, on that side of it. The perception side, not so much. I would say on the perception, it didn't require a whole bunch of understanding on the robotic side. So I'd say 50-50. I would say 50% of the project, or I'd say 30% of it is probably motion planning, 30% was perception, and then the other 30% was just integrating the system, the high-level architecture, the high-level controlling the process through the state machine, all of that. So I'd say 30, yeah, 30-30. Oh.
Good. Quick question. Have you guys considered using physics as a physics simulator?
We have, I guess the question is, has we considered Gazebo as a physics simulation? We looked at Gazebo, but right now we haven't used any of our need for the physics side of it. We've mainly been doing just collision checking for that. So we do use it in the sense for our sensor simulation. So we can have a hybrid system running because it has really nice tools for sensor simulation and things like that. We have talked about it for the festooning. But there's a challenge on how do you incorporate that in motion planning, because it's actually where you start and how you progress through the motion. You would have to model it, and that's not how the current motion planners work. They're kind of just sampling all over or optimizing the whole trajectory. So there is interest, but we have not.
I think if anyone wants to get into physics modeling of festooning, you would have a very interested partner set down here.
Yeah.
For sure.
Yeah.
On the gantry system, what was the application?
On the 2-axis gantry, it was, so you asked on the 2-axis gantry system, what was the application? I believe that was chemical stripping.
Correct.
Process.
Okay. So you talked about a lot of different tools used to create a clean image of the part, right? There's a lot of filtering.
Mm-hmm.
Is that something that's done once and then can be used for all the parts that you're going to put in front of the cell?
In this application, I believe that was the case. We were able, for the types of parts that were coming into this cell, we were able to generate a single set of filters that the data needed to run into because the sensor wasn't changing, and the only thing in the environment was the part, so we were able to use a single set.
So similar with the high mix low volume application need?
Yes. Yep.
And so what was the development effort to get that system in a running state?
You want to answer?
Well, let's just say that particular system, it went from, so basically a preliminary kind of, let's just say, software. So we did integration, and then it was commissioned probably in a period of, now mind you, there was tear down at the integrator site, shipment, reset back up, but it was about 8 weeks.
That's including all the software?
Well, so the initial, to get the preliminary, like let's just say first pass software before it went on hardware, was probably combined effort another 6 weeks. But yeah, that's total effort, right? So that obviously went over a calendar time with like, oh, we're jumping off of this for a little bit.
Yeah, it was an interesting situation. We had to move fast.
Yes.
for that project.
Any other questions for Levi? Oh.
So I saw for Tesseract, it looks like you guys have some ROS-I support.
Yep.
that include, like, the ROS industrial driver, simple messages, all that other stuff? Is that ported yet?
That has not been ported yet. I think in most of those systems, we haven't needed that portion of it for the ROS-II applications. We've talked about it, but I'm not sure that's going to be needed. Once we move to ROS-II, there's some questions on if that will be, but it has not been ported yet.
Yep.
How far into the controller, the robot controller, did you guys interface? Were you, was it a strategy level, joint level, wire point?
So the question was, how far did we get into the controller on these implementations? In this case, we found it was easier to, and it depends on the manufacturer, but on this case, what we were doing is we were generating the robot trajectories. We would then write native robot programs and then FTP those to it. Then the PLC would execute a high-level program that would go through these sequence of programs to execute the overall process. Yes. Yeah. And we found that works really well. And that was the other reason behind the contact monitor, is because it should follow very closely to what we did for the motion planning. But we wanted to ensure that, so we have some type of contact monitor running throughout the whole process to make sure that it is following our trajectory. It's not going to collide with something, and if it is, it will halt the process.
Excellent. So yeah, I mean, I think that's a really interesting point about the robot controller, right? So depending on your, let's just say, the peculiarities of your specific hardware selection, there are a number of different ways to set up this type of system to take advantage and leverage it to its, let's just say, best utility in the most reliable fashion.
Yeah.
So in this particular configuration, this sort of, if you will, post-processing it into FANUC native code was the optimal solution. Yep. Right, but for those of you maybe who have been engaged with some of the work out of the ARM Institute, they were able to leverage, let's just say, some external guided motion to do like much more low, like on the servos, essentially, actuation for precision part placement. Again, different OEMs offer different solutions, and you can optimize your system, reconfigure it based on what's been presented to you.
Yep.
All right, if there's no other questions, Levi will be here throughout the day. He'll also be one of our tour guides, so thank you, Levi.
Thank you.